කීම් කියලා බැලුවේ. He didn't. Okay. හරි. Okay, unmute. Yes, we need to enable the Colombian. What's the name? Aniket then. Then okay, मैं ना हो गया है But making it like really easy with that. All right, people, kindly mute your mics first. But like before that, like, are there anyone who have difficulties in logging to the WebEx thingy today? Because yesterday only 100 of you all could log. There are 136 of students now. So are there any students who have difficulties in logging today for the to the WebEx? Ayo, can someone talk? Can someone talk and confirm that all the students could log into WebEx today?
Sir, a few people don't have electricity, so they couldn't join.
few of them do not have electricity. Is that what you said?
Yes, sir.
Few of them, like so I hope like except them others can join, right? Because today you
Yeah,
don't
I
have
think so.
the limitation for that goes only for 100. Only 136 students can join. Ten at the moment, so let's go and start the work. Other people can join meanwhile if they want to. Um, right. Before starting the session, guys, kindly mute your mics. If you have questions, keep them like written somewhere or in your mind. So at the end of the session, when I give you enough time, you can ask from me. So during the session, I don't want to hear any background noises because you have not muted your mic. So you have to mute your mic. And in the same time, if you have questions, you're going to get a time to ask the questions, right? Okay, now I'm going to write something on the board. I want you all to confirm that the picture is clear to you, right? I'm going to write the same thing that I wrote yesterday. So now look at this and confirm me whether it is clear or not. I want someone to talk, but I'm
Yes,
asking, is this clear to you or not?
yes, sir,
Yes,
it's clear.
yes, sir, it's clear.
All right, sweet. Hold on. Let's begin it now. All right, good afternoon, everyone. Today we are going to do an experiment which is totally new to you. I know you all are very familiar with titrations by now. You have done enough titrations on acid-base titrations, I mean acid-base chemistry. But today we are going to move to a new section of titrations. They are called redox titrations. I know this word is not new to you. You know this word, redox. It comes as reduction and oxidation. Redox. This comes from reduction and this comes from oxidation. Right? So we are going to do a redox titration today. Basically, one species is going to reduce and the other species is going to oxidize during the titration. And similar to the acid-base titrations, we are going to get an endpoint. And using the burette volumes, we are going to calculate the unknown concentration of a species. That's the base of the today's experiment. So, what is reduction and what is oxidation? From the basic knowledge, you know that reduction is a species undergoing the reduction by gaining electrons. So if there's a species like A, if it gains electrons and it goes to its form, so it is the reduction. It has gained electrons. A has gained electrons to reduce. In the same way, so this is the reduction. In an oxidation, say that B oxidizes, it releases electrons. It releases electrons and move to a positive state, and this is called the oxidation. So keep it in your mind. In a reduction, the particular species gain electrons, and in an oxidation, a particular species release electrons. Right? Okay. That's the basic. Now we are going to move to the real chemical species and see what we are going to do today. Today we are going to do a titration in between potassium permanganate and oxalic acid or sodium oxalate. So we have two species. What are they? Potassium permanganate. What is potassium permanganate? That purple color solid that you normally call as conjus. Okay, the chemical name of that particular compound is potassium permanganate. So the chemical formula for that is potassium permanganate. And we have sodium oxalate, Na2C2O4. This is going to reduce and this is going to oxidize. What is going to reduce? Potassium permanganate is going to reduce and oxalate of sodium oxalate, sodium oxalate is going to oxidize, right? So let's see how are we supposed to write the half reactions. Now we get the permanganate ion. What is the oxidation state or the oxidation number of manganese in permanganate ion? I know this, you will have done A levels, you know how to calculate the oxidation number. So with your previous knowledge, the oxidation number of manganese in permanganate ion is +7. During this reduction reaction, now this is the reduction and we call it as a half reaction. During the reduction, permanganate ion reduces to manganese. It's Mn2 plus. So obviously the oxidation number over here is +2. For this particular species, permanganate to reduce to Mn2 plus, it has to gain 5 electrons. Right? So it is gaining electrons, it is reducing. In this particular half reaction, when we write it, we know that it is unbalanced in terms of oxygen. So we have to add 4 water molecules, and to balance the protons, we have to add 8H plus. I know this reaction is not that new to you. You have written this reaction many times, but it's good to recall. So permanganate ion reduces to give Mn2 plus. It gains 5 electrons during the reduction, right? All right, now I'm going to write the oxidation reaction. It is again a half reaction. Oxalate ion C2O5 C2O4 2 minus. It goes to carbon dioxide. The first thing that you have to do, you have to balance the number of carbons. Now here you have only one manganese and one manganese at either sides. But here you have 2 carbons over here and you have to add 2 carbons over here. Now what is the oxidation state over here, oxidation number over carbon? It's +4. Then how do you calculate the oxidation number in C2O4 2 minus? That is +6. So you are getting 2 electrons over there, and that is the oxidation half reaction. You don't have to read it, write it down because you are going to get the recorded video. Then when we write the full reaction, it's permanganate ion plus you have the 8H plus and oxalate. It gives you Mn2 plus and carbon dioxide. I'm not going to write the whole reaction because I'm going to keep that work for you. Now you know how to write the half reactions, and from that get the total full reaction. Only thing what I want to tell you is that permanganate reduces and oxalic acid or the oxalate ions oxidizes. So that is the basic of today's experiment. Guys, if you all can remember, when we were doing acid-base titrations, we used an indicator. Phenolphthalein, methyl orange, bromothymol blue. Why did we use an indicator? Because we wanted to indicate the endpoint. We want to, like, how do we indicate the endpoint? By simply getting a color change. We used colorless solutions. Can you all remember? Acids and bases, they were colorless. So to indicate the endpoint, we had to add a colored reagent, which is a weak acid or base, an indicator. But during this particular titration, permanganate oxalate acid oxalate titration, we don't have to use an indicator. Now, the reason is permanganate ion has a color. What is the color? Purple color. But what is the color of Mn2 plus? Colorless. So at the end point, in the titration flask, you have the oxalate ions. And in the burette, you have the permanganate ion. So when you add permanganate dropwise into the oxalic acid solution, this is transparent and this is purple. What at the end point, the color of this particular solution will turn to from colorless to faint purple color. Why? This is transparent, and at the end point, all the oxalate ions are consumed during the reaction. So at the end point, you don't have any oxalate ions. So when you add another drop of permanganate ion, the color of the solution turns to kind of slight purple color. Why? Because to react with that drop of permanganate, you don't have enough oxalic acid present in the flask because all the oxalate ions have been consumed, have been neutralized. So that's why we are not going to use a particular external indicator because it say that permanganate ion act as a self-indicator. And for the reaction, we add sulfuric acid. If you go through your lab guide, which is given to you now, we add a particular volume of sulfuric acid that is to provide the necessary H plus because we want an acidic medium to run the reaction. If you really look at the half reaction, if you can recall that, H plus was there at your left-hand side, which means that you want an acidic medium for the reaction to happen. So to give that acidic medium, we have to add sulfuric acid. And if you really go through the protocol, if you given in your lab manual, you can see that at one point you have to heat the solution. Why do you have to heat the solution? This reaction is not favorable at room temperature. We have to supply the particular activation energy. In order to supply the activation energy, we have to heat the titration flask with the oxalate ions. So these things you have to keep in your mind because if you really look at the post-lab questions that I have given to you in the lab manual, you have to answer those questions. To answer those questions, you have to know these points. So that's the basic theory behind today's experiment. And let's do the experiment and see how it goes. Okay, so the first thing that we are going to do is to fill the burette with potassium permanganate solution. Now you can see it as like a purple color solution. So to do that, the first step is to lower the position of the burette, and then you input the funnel, and then you fill it with, you make sure that the tap is closed, and then you fill it with potassium permanganate. Right. Now we have filled it with potassium permanganate. And you then raise the burette. Right. Then next thing is you take a titration flask and you get 10 cubic centimeters of oxalate solution. To do that, you have the oxalate solution in the volumetric flask, and then you add some volume to a cleaned beaker. Then you take 10 milliliters of the oxalate solution by using the graduated pipette. Then you transfer it to the titration flask. Right? Then you have to add 5 cubic centimeters of the sulfuric acid given to you. Then you add the 5 cubic centimeters of the sulfuric acid into the oxalate solution. And next thing is, if you really look at your lab manual, you can see that after adding the sulfuric acid, you have to heat the solution for at 60 degrees for few minutes. So this will take a little while. All right, till we heat the solution, if you have any questions, you can ask from me. Are there any questions? Because we are waiting till the solution gets heat up, right? So if you have questions, you can ask.
So is there having any specific temperature to heat?
Normally it goes to like 60 degrees, not beyond that.
Okay, sir. Thank you.
Welcome. Are there any other questions? Guys, if you have any questions, you can ask. Because I'm waiting till this solution heats up. Hmm? All right. All right. Till it heats, we can read the initial reading of the this thingy, the potassium permanganate. For that, you have to use a flashlight or simply a candle. And because that is a purple color solution, we can't like really see that. So we can get it as 4.9. So the initial burette reading is 4.9. All right, let's do the titration now. In the one that you got. So like it has not been heated up properly. All right. We'll wait a little bit. Huh? Let's do it again and see. Now you can see that when I add the drops of potassium permanganate, the the purple color fades out when it reacts with oxalic acid. As you can see that I have to add the drops very slowly because I have to identify the endpoint. To identify the endpoint, what is the color? It's colorless to faint purple. So you can't keep adding drops. Like you have to add one drop and let it to react, and then this next drop. Guys, now you all can see that like initially the drop of the permanganate reacts very like when in a high speed, but now it takes some time to react. You can see that the purple color takes some time to fade out. The reason for that is now you don't have much oxalic acid in the medium to react, so the reaction rate has been slowed down a little bit. All right, now you can see that a light purple color, which is the endpoint, and make sure this particular purple color is not going to remain there for a long time. With time, let it can fade it out because of the other atmospheric conditions. But if it persists more than 30 seconds, like about 1 minute, that there you have reached the endpoint. So now here we have reached the endpoint of the titration. So basically, you know that in a titration, we have to duplicate. We have to do two trials. As it is a video, I'm not going to do both trials. So, but still, again, that policy is there, that principle is there. In a titration, you have to do two trials. Why do you have to do two trials? You have to get the burette readings, the two burette readings, and then you have to compare them. If the difference between the two burette readings exceeds zero point 0.5, then you have to do another trial and get it lesser than zero point 0.5. Then you have to use those two readings, the correct two burette readings, to calculate the concentrations. But here, as it's a video, I'm not going to do the second trial because it's the same thing that you will be observing. Now, I told you that in this particular titration, we are not going to use an external indicator because potassium permanganate acts as a self indicator. Guys, what really happens in the titration flask is that when oxalate ions, actually could be oxalic acid, the oxalate ions completely react with the potassium permanganate. At the end point, you don't have oxalate ions as well as you don't have permanganate ions. So what do you have at the end point? Carbon dioxide molecules that dissolve in the aqueous medium and the Mn2 plus. So do we know whether we have reached the endpoint by that colorless solution? No, we don't know. So we may have to add 1 or 2 drops of potassium permanganate to identify the endpoint because potassium permanganate is the self indicator. Now, that number of drops that you have to add could be 1 to me, could be 2 to another person, could be 3 to another person. So to identify the number of drops, number of potassium permanganate drops that you have to add to identify the slight purple color, we have to do a blank titration. Now, what is a blank titration? I told you the purpose of the blank titration is to identify the number of potassium permanganate drops that requires to identify the particular slight purple color. That varies from person to person. To identify that number of drops, we have to do a blank titration. And in a blank titration, we don't have the particular analyte of interest. So what is the particular analyte of interest of the solution that is in the titration flask? That is the oxalate ions. So we have to prepare a solution without the particular analyte. So what should be the solution without the analyte? It should be 10 cubic centimeters of deionized water with 5 cubic centimeters of sulfuric acid. Let's do that particular blank titration. So you get a titration flask and you have the distilled water bottle over here, and you get a beaker, and then you add some distilled water into the beaker. And similarly, you get 10 cubic centimeters of deionized water into the graduated pipette. And then you release it. You transfer it to the titration flask. Keep it side, and then you take the sulfuric acid bottle. Now, what is the volume of sulfuric acid that we are supposed to add? 5 cubic centimeters, same as for the analyte. And then you transfer that sulfuric acid into the titration flask. Right. You keep the filler away, and then you close the bottle. Right. Before that, the final reading of that particular titration is 15.2. The final reading of the burette is 15.2. Right, now we are going to do the blank titration. Now, what do you have in the titration flask? 10 cubic centimeters of deionized water and 5 cubic centimeters of sulfuric acid. Here, you don't have the analyte. What is the analyte? Oxalate ions. Now, we'll see, we have to slowly add 1 drop first, and you stop it, and you swirl it. Now, guys, can you all see that? From a 1 drop, I could see the slight pink color. It could be 2 drops to you. It depends on the person who do the titration. But we have to know the number of drops of potassium permanganate that was consumed to give this particular slight pink color. So that particular volume, the volume of a 1 drop, should be subtracted by the volume transferred to identify or to determine the volume of the potassium permanganate consumed to neutralize the or react with the oxalate ions. If I say it again, now you have a particular burette reading for the reaction, potassium permanganate and oxalate acid. And then you know the number of drops that was consumed for the blank titration. You have to subtract the volume of a drop from that particular volume transferred to identify the correct volume reacted or correct volume reacted with the oxalate ions. So that is the particular titration that we were supposed to do today. With that, if you have any questions, feel free to ask from me now. So today experiment was between potassium permanganate and oxalate ions. So now it's your time to ask questions from me.
So the volume in the titration flask is 15 cubic centimeters or 10 cubic centimeters.
Say it again, I didn't get you.
Volume of the titration flask is 15 or 10 cubic centimeters because we are doing 5
You mean,
H2SO4.
you mean the volume of the oxalate ions that I used?
Yeah.
10 cubic centimeters.
And for the calculation, we have to take 15 or 10.
No, it's like this. Now, I used 10 cubic centimeters of oxalate ions and 5 cubic centimeters of sulfuric acid. So for the calculation, what matters is the number of moles or the amount of oxalate ions. Sulfuric is not accountable for that.
H2SO4 is added only to fasten the reaction or give the H plus.
To provide the acidic medium required for the reaction.
And when performing the reaction, the temperature is reduced when we are titrating. So do we have to heat it up again when we are doing titration?
I can't hear you properly. Can you repeat the question again?
Firstly, we heat up the solution to 60 degrees. But when you are
Right.
performing the titration, the temperature reduces again. Do we have to heat it up or again? I mean,
not necessarily, because that temperature is like that 60 is a kind of like an arbitrary value. It can be 55 or it can be 65 as well. So during the reaction, the drop of the temperature in the reaction medium is not that much. It's not considerable. So you don't have to really heat the reaction again.
Thank you, sir.
Sure. Guys, it's your time to ask questions.
And the KMNO for concentration?
The KMNO for concentration is 0.02 grams per liter. I'm sorry, it's 0.02 moles per cubic decimeter. It's not grams per liter. Again, if I say it like the concentration of potassium permanganate is 0.02 moles per cubic decimeter. Any questions? I can hear only one voice. There have to be like 136.
Sir, what is the final butyl reading?
That was 14. I'm sorry, 15.2. So make sure that you have to subtract the volume of a drop
Thank you,
from
sir.
that reading.
But sir,
You have to subtract the volume of a drop from that reading. So you know what is the final volume. You know the initial volume. When you from that you can calculate the volume transferred, right, for the reaction. And
in
that
acid-base
say that is 10 cubic centimeters.
subtract a drop of volume
For
or
an
something like
example,
that.
say that the volume transferred is 10 cubic centimeters. From that 10 cubic centimeters, you have to subtract the volume of a drop. Now, what is the volume of a drop? Someone answer me.
0.05.
Very good. Say 0.0 cubic centimeters. So that particular volume has been consumed to identify the color, not for the reaction. That's why we did the blank titration. So you have to subtract a volume of a drop which is 0.05 cubic centimeters, from that calculated volume transferred, which is 10 cubic centimeters. So it's like 10 minus 0.05 is the actual volume consumed for the reaction. Guys, any more questions? I'm happy to answer.
So in the acid-base titrations also, we might add a few drops more to identify the color, but there we didn't do a blank titration or anything like that.
Very good. In an acid-base titration, we used an external indicator, right? Phenolphthalein or methyl orange or bromothymol blue or something like that. So that is an external indicator that we use to indicate the endpoint. So we did not alter the volumes of the reactants over there. But here, as potassium permanganate acts as the self-indicator, to give that light purple color, we have to know then what is the number of drops that it has been consumed. To identify that, we perform the blank titration. Is that clear to you?
Yes, thank you.
Sure. Any more questions? I'm happy to answer. Please ask.
So when we are calculating the concentration, we have to consider on the full equations between the reactions. So
That's true.
actually, do we have to build up it when we are writing our lab reports or something?
Yes. Now you know what's the half reaction. What is the half reaction like of the potassium permanganate, and you know the half reaction of oxalate ions. So by using those two, come up with the full reaction. That is your homework. I have like helped you for a certain, I would say like 80% I have helped you. That rest of the 20% you have to do. So come up with the full reaction and look at the stoichiometry, and from that calculate the concentration of the oxalate or the sodium oxalate that we used. You have to know the stoichiometry between the potassium permanganate and the oxalate. To calculate the stoichiometry, you have to write the balance reaction, balance full reaction by using the half reaction. And once you know the stoichiometry, as you know the amount of potassium permanganate that has been consumed for the reaction, you can automatically calculate the oxalate, the amount of oxalate over there, and from that you can calculate the concentration of that, because you know the volume of that particular oxalate solution as well.
So actually, what is the actual concentration of the sodium oxalate?
That is 5 into 10 to the negative 2.
So sorry.
5 into 10 to the negative 2. If I say it in normal words, it's like 0.05.
Okay,
0.05 moles per cubic decimeter. If I say it in the scientific notation as the standard method, 5 into 10 to the negative 2.
So in this case, actually, when we are calculating the endpoint, actually when we are getting the endpoint, it can be very person to person, because actually we are not using the external indicator. So how actually that we are minimize the error?
So, can you repeat the question? Your voice was not that clear to me.
So actually in this case, because that we are not using the external indicator.
Right.
So we are just using the KMNO4 as indicator, because in the same case. So when we are getting the endpoint, it can be vary, because some person can add 1 drop, some person add 2 drops, and some person can add 3 drops. So it can actually it can affect to the reaction or endpoint. So how can we minimize these errors?
No, like it's like this. That's why we perform the blank titration. Now, like my sensitivity is different from your sensitivity. So to identify the color,
one group, some person had two groups, and some person
right?
had three groups.
So
Actually, it can
if
affect to the
I would
reaction.
add one drop and you would add two drops. So that's why we perform the blank titration, and then we can subtract that particular volume from the actual volume. So there won't be any error in the calculation. To identify the color. Is that clear to you? Right? So if I would add one drop and you would add two drops. So that's why we perform the blank titration, and then we can subtract the particular volume from the actual volume. So there won't be any error in the calculation. Is that clear to you?
Okay, thank you, sir.
Sure. So are there any other questions? If it is not, then we can wind it up. All right, seems to be there are no questions for me to answer. So like, make sure that I will email you the worksheet. I want the completed worksheets right after your exams, because I understand this is time that you are studying for the exam. So I will email the worksheet to you, do all the calculations, fill the worksheet, and send it to me right after your exams. All right, thank you for participating. Right, bye-bye.